The equation is E equals mc squared. You've probably heard of it. Einstein figured this one out back in 1905, and people often think it's just about nuclear weapons or nuclear power. But it's actually telling us something much more fundamental. It's telling us something about the speed limit of the universe itself. Let me start by asking you a simple question. How fast can something go? Well, in your everyday experience, you can go faster than a bicycle. A bicycle can go faster than a person walking. A car goes faster than a bicycle. You can always go faster if you have enough power, enough fuel, enough energy. Intuitively, it feels like there's no speed limit. Just keep pushing, keep accelerating, and you'll go faster. But that's not true. There is a speed limit. And it's not a law that somebody made up. It's built into the fabric of space and time itself. That speed is the speed of light. Light travels at about 186,000 miles per second. Now, let me just stop and let that sink in for a moment. 186,000 miles per second. That's fast enough to go from here to the moon in about 1 second. It's fast enough to circle the Earth 7 times in just 1 second. Now, Einstein discovered something extraordinary. He discovered that nothing with mass, nothing like you, me, a spaceship, an atom, anything with mass, can actually reach the speed of light. And this isn't because we haven't invented good enough rockets yet. It's not a limitation of our technology. It's a fundamental law of physics. It's built into the way space and time work. So why is this? Well, this is where E equals mc squared comes in, and I want to explain this to you in a way that makes sense. Imagine you're trying to accelerate a spaceship. You push on it with some force. It speeds up. Good. Now, you keep pushing. It speeds up more. Keep pushing. Still works. But here's what's strange. As you get faster and faster, as you approach the speed of light, something peculiar happens. The spaceship doesn't just get faster in the way you'd expect. Instead, it becomes heavier, more massive. Think about it this way. You're putting energy into the spaceship to accelerate it. That's work. That's energy going into motion. Well, Einstein showed us that energy and mass are actually the same thing. Energy has mass. When you add energy to something, you're adding mass to it. The equation E equals mc squared tells you exactly how much. Here's the important part. As you approach the speed of light, you have to put in more and more energy to make it go just a little bit faster. And because that energy has mass, the spaceship gets heavier and heavier. The closer you get to light speed, the heavier it gets. At the speed of light itself, it would be infinitely heavy. You would need infinite energy to get it there. This is why I said nothing with mass can reach light speed. It's not possible. It's not that it's hard or expensive or requires technology we haven't invented yet. It's impossible in the same way that a square circle is impossible. The laws of physics forbid it. Now, you might be thinking, well, okay, maybe we can't quite reach light speed, but we could get pretty close, right? We could go 99% of light speed. That's still pretty fast. And you're right, you could in principle get very close. But here's the catch. Even getting to 99% of light speed requires an enormous amount of energy. Let me give you some numbers to illustrate this. If you wanted to accelerate a spaceship the size of a large building, something that could actually carry people and supplies, to even half the speed of light, you would need energy equivalent to thousands of nuclear bombs. And this isn't some rough estimate. This is what the physics actually tells us. The energy requirements are truly staggering. But okay, let's set that aside for a moment. Let's imagine that somehow, through some incredible future technology, we could accelerate a spaceship to a decent fraction of light speed. Let's say we could get it to 90% of light speed. Could we then visit other stars? Well, here's where the second problem comes in, and this is about distances. The nearest star to us is Proxima Centauri, and it's about 4.3 light years away. Now, what does that mean? It means that if you could travel at the speed of light, which, remember, you can't, it would take 4.3 years to get there. 4.3 years, just to the nearest star. But we live in a galaxy with hundreds of billions of stars. Most of them are much, much farther away than 4.3 light years. The center of our galaxy is about 26,000 light years away. That means if you traveled at light speed, it would take 26,000 years to get there. And then there are galaxies. Our nearest large galaxy, the Andromeda Galaxy, is 2.5 million light years away. If you could travel at the speed of light, it would take 2.5 million years to get there. These numbers are incomprehensibly large. A human lifespan is about 80 years. The entire recorded history of human civilization is only about 5,000 years. We're talking about times that are millions of times longer than the entire existence of human civilization as we know it. Now, I know what some people think. They think, well, maybe aliens have discovered some trick. Maybe there's some way around this. Maybe they can go through a wormhole, or they've figured out some shortcut through space. These are wonderful ideas, and physicists have actually thought about them. There are solutions to Einstein's equations that allow for things like wormholes. But here's the problem. Even if they exist, and we're not even sure they do, they would require exotic forms of matter that we've never observed. They would require negative energy, which we don't know exists. And even if you could navigate a wormhole, you'd have to deal with forces that would tear any spaceship apart. So these aren't really practical solutions. They're mathematical curiosities. Let me give you another perspective on this problem. Let's think about it from the point of view of a civilization trying to visit us. Imagine there's an alien civilization somewhere in the galaxy. They're intelligent. They're advanced. Let's say they're 1,000,000 years ahead of us technologically. Maybe they figured out some incredible things, but they still have to obey the laws of physics. They still can't go faster than light. They still have to deal with these enormous distances. If they're 100 light years away from us, and they want to visit Earth, they have to travel at least 100 years just to get here. That's a journey that's longer than the entire history of the United States. And that's just for the nearby aliens. If they're 1,000 light years away, it's 1,000 years. If they're as close as you can reasonably expect, say, a few hundred light years, we're talking about centuries. Now, you could imagine a civilization that builds a generation ship. A ship so large that people can live on it for centuries, and they raise their children, and their children raise their children, and after many generations, their descendants arrive at Earth. This is theoretically possible, but it's impractical. It requires an incredible commitment of resources, and the civilization would have to maintain a functioning society on a spaceship for hundreds or thousands of years. But there's another issue. Even traveling at a high fraction of light speed, there's the problem of collisions. Space isn't completely empty. There's dust. There's hydrogen. There are small particles. At 99% of light speed, a grain of dust hitting your spaceship would have the energy of a bomb. You'd need massive shielding just to protect yourself from the interstellar medium. And then there's time dilation. This is another consequence of relativity that I should explain. When you travel at speeds close to light speed, time moves more slowly for you than it does for people on Earth. It sounds like science fiction, but it's real. It's been measured. Astronauts in space age just slightly slower than people on Earth, even though they're only traveling at about 18,000 miles per hour. If you traveled at 99.9% of light speed, your clock would run very slowly compared to Earth time. A journey that takes hundreds of years from Earth's perspective might take only a few years from your perspective. This seems like it could solve the problem. But there's a catch. When you arrive, you'll have only aged a few years. But thousands of years will have passed on Earth. Everyone you knew is dead. The entire civilization might have changed. Technology might be completely different. So even if a civilization managed to make the journey, what would they find when they arrived? Would Earth still exist? Would there still be humans? Would humans even be interested in making contact? Now, let me come back to the core issue, because I want to make sure you understand why this equation, E equals mc squared, is really the answer to your question about alien visitors. The reason is this. The speed of light is not just a number. It's not just the fastest speed that happens to exist. It's a fundamental property of space and time. It's woven into the fabric of reality. And it's there because of conservation laws, the laws that govern how energy and momentum work. Einstein's equation E equals mc squared tells you that energy and mass are two names for the same thing. When you accelerate something, you give it kinetic energy. According to relativity, this energy has mass. As you go faster, you gain more kinetic energy, which means you gain more mass. At light speed, this effect becomes infinite. The mass becomes infinite. The energy required becomes infinite. And this is why light speed is a barrier that cannot be crossed. It's like asking, can you reach a temperature below absolute zero? The answer is no. Not because we haven't invented the right refrigerator, but because that's not how temperature works. Absolute zero is the lowest temperature possible because it's defined as the point where all thermal motion stops. You can't go below that because there's nothing below zero motion. In the same way, light speed is a barrier you can't cross because of how space and time and energy work. So here's what this means for alien visitors. They're not coming here. If they exist, and I think it's quite possible that life exists elsewhere in the universe, they're probably not going to show up at Earth. The distances are too vast. The time required is too long. The energy required is too enormous. Now, could they visit us in some other way? Could they send signals? Could they send robots? Could they send some kind of transmission? Well, signals travel at light speed. So if they're thousands of light years away, it would take thousands of years for a signal to reach us. We could receive a message that left their planet thousands of years ago, and any reply we sent would take thousands of years to reach them. A conversation would be impossible in any practical sense. But what about robots or probes? Could they send self-replicating robots that populate the galaxy and visit every star? This is an interesting idea, and theoretically, it might be possible, but it still requires crossing these enormous distances. Even if the robots could travel at a reasonable fraction of light speed, say 10 or 20% of light speed, they'd still take thousands of years to travel between stars. And they'd have to be incredibly sophisticated to repair themselves and build copies of themselves for millions of years. It's theoretically possible, but it's so impractical, so difficult, so resource-intensive, that it seems very unlikely. Here's what I think is the real answer to the question of why we haven't been visited by aliens. It's not because aliens don't exist. I think they probably do. It's not because aliens are afraid of us or uninterested in us. It's simply that space is too big and time is too long. The laws of physics make travel between the stars practically impossible. The universe is so vast that if intelligent life exists elsewhere, they're almost certainly too far away to ever make contact with us. We might be alone in our local region of space. And even if intelligent civilizations exist throughout the galaxy, they're probably isolated from each other by distance and time in a way that makes meaningful contact impossible. This is actually a profound answer to something called the Fermi paradox. The Fermi paradox is the question: if the galaxy has billions of stars, many with planets, and many of those planets potentially habitable, why haven't we detected any aliens? Why haven't they visited us? And I think the answer is because the universe is too big. Einstein's equation isn't just telling us about nuclear energy or mass energy equivalence. It's telling us something about the structure of the universe itself. It's telling us that nothing can go faster than light, and that light speed is an absolute barrier. And this barrier, combined with the vast distances between stars, makes the galaxy a place where civilizations are isolated from one another. Now, this might sound depressing, but I actually think it's beautiful. It means that Earth is special in a way. We're isolated. We're on our own. Whatever life exists here, whatever intelligence develops here, it has to develop on its own terms, without interference from other civilizations. We have the chance to figure things out for ourselves. And who knows? Maybe that's the real answer to the Fermi paradox. Maybe every civilization that develops in this universe is necessarily isolated by the laws of physics. And each one has to figure out, on its own, what it's going to do with its planet, with its star, with its own little corner of the universe. The equation E equals mc squared, which was developed to understand the nature of light and energy, ends up telling us something profound about our place in the cosmos. It tells us that we're alone, not in a sad way, but in a way that means we're responsible for our own destiny. And I think that's a pretty remarkable thing to learn from a simple equation.